Hello, and welcome back to the channel Tech Study Circle. Today's problem we have is craft a near real-time system for monitoring metrics like count of views on YouTube, count of likes on YouTube, count of dislikes on YouTube. Consider a view to be counted when a video has been watched to at least 10% of its total duration. System objectives. Near real-time count. Since we are counting the views, likes, and dislikes of a video, it is crucial that the count should be updated in real time or near real time. An outdated count could hamper the user experience and could also impact the reliability of the system. The system needs to be highly available. If a video gets viral and there are a huge number of requests to view or update the stats, the system should not go down and should be able to handle this load. The system should be fault tolerant. Failure of a component of the system should not impact the overall functionality. High consistency. The system should maintain a high level of consistency. If a user views, likes, dislikes a video, then that should be reflected across all servers soon to avoid any discrepancy. The system should be designed in such a way that scaling should be possible horizontally and vertically. This is to ensure that, as the system grows and there are more videos and more stats to be handled, the system should not become slow or unresponsive. So we should make sure we confirm if it's okay to have eventually consistent system, or we need real time, which could be needed for different use cases such as financial reporting. We can also clarify the SLA, that is, once the user views a video, how long before it gets reflected in counter. Ideally, it should be below few seconds, but we should define a SLA. Our system should support multi-regions, and we can clarify this will be handled. Ask the usage of the counters. Will it be used for reporting or displaying the counter on the videos? Based on the usage, the system design could change. Hence, it's important to understand the usage of the system. Estimation of scale. It is important to understand and estimate the potential scale of the system. This involves calculating potential data sizes, the amount of requests per second, minute, hour, peak and off-peak loads, and storage requirements. Approximately 500 hours of video are uploaded on YouTube every minute. Assuming on average each video is watched for 10% of its duration and it triggers a view, YouTube gets 960,000 views per minute or 16,000 views per second. For the likes or dislikes count, consider an assumption that only around 5% of viewers actually react to the video, either with a like or dislike. Therefore, the application should be ready to handle around 800 likes, dislikes per second. If we assume each count, view, like, or dislike, requires about 1 byte of storage, with just views alone, we're looking at 16 kB of data per second, or approximately 1.3 terabytes of data per year. And if we consider likes, dislikes, the number would approximately double. This scale gives us an understanding of what technologies, data, and infrastructure to consider, such as NoSQL databases, distributed computing, and cloud API storage. Design. We need APIs for two main types of interactions. The first set of APIs will support clients, such as desktop and mobile applications, to increment and retrieve the count. The second set will facilitate internal microservices to communicate with each other for synchronization and data propagation. Public APIs should be RESTful because of their stateless operation, cross-platform compatibility, and easy debugging. Let's say, for incrementing the view count, a POST API is needed. To retrieve the views count, a GET API would be used. This API will return the current total views of the video identified by 1234. Internal microservices APIs. For internal services to communicate with each other, we will use HTTP-based POST APIs. An example of such an API, propagate count. This API will be called by the primary view counting service to communicate incremental view count to its replicas. High-level system design. The process begins with the user's interaction with the user interface, UI. Whenever a user clicks like on the video or watches a video for at least 10% of its total duration, a service hooked to the UI fires a request with the respective data. This data is sent to the load balancer. The LB strategically distributes the load by routing the requests to the application servers. The role of this LB is crucial to ensure high availability, scalability, and reliability of the system, since it acts as the work distribution system. The request, after being processed by the application server, is converted into a concise message which is pushed into the message queue system. This message queue system operates to queue the requests to ensure that our back-end systems aren't getting overwhelmed by the large number of requests being received. Having a message queue acts as a buffer, allowing the system to handle peak traffic conditions. Allows the system to handle high traffic conditions by queuing requests for processing and prevents the system from getting overwhelmed with incoming requests. The back-end processing service pulls the messages from the queue and processes it. The processing involves extracting the necessary data from the messages and make the required updates or counting operation in the data store. The data store here includes the database and the cache. The count, increment, and decrement are processed by the back-end service, and the tallies are updated in the database. Here, caching would be used to speed up the response time by keeping highly accessed count results, like views, likes, and dislikes, in memory or external caching systems. For storing the count data, a distributed data store like Apache Cassandra can be used. The main reason behind this choice is that it allows flexibility in horizontal scaling, which is what we need for dealing with such high-scale systems. Let's define the data model. The entities under consideration would primarily be video and user. The video entity will have attributes like video ID, which will be unique, title, upload date, description, likes, dislikes, and views count. For the purpose of counting views, likes, dislikes, we can structure the data as follows. View count, a key value pair where video ID serves as the key and views count as the value. Anytime a user watches 10% of the video, the view counter against the video's video ID gets incremented. Two separate key value pair where video ID is the key and likes or dislikes serve as the respective values. These get updated when a user likes or dislikes a video. The key value data model enables fast lookups and updates, which is beneficial for our use case of high-frequency counting operations. The user entity will hold details of the viewers such as user ID, username, registered on, email, etc. Caching. To serve requests faster, caching can be done at multiple levels. On the server side, we can cache the frequently accessed data, view counts, or likes counts in memory or memcached. This reduces database calls, ensuring faster response times. Content Delivery Networks, CDN, can also be employed to cache the video and related content so that users get a quick response. You can also use Redis to cache data due to its high-speed performance and support for various data types. Data consistency and integrity. Eventual consistency. We can implement an eventually consistent model using distributed databases like Cassandra. In this model, the system agrees to tolerate temporary inconsistency between replicas in favor of availability and partition tolerance. Write operations are typically acknowledged before replicating the data to all nodes, leading to temporary inconsistencies. However, the system guarantees that given enough time without further writes, all replicas will eventually have the same data. The downside of this approach is that the client can read stale data. However, in our system design, reads are far less frequent than writes due to the nature of counts recording, making eventual consistency an acceptable compromise. For the security and privacy. Rate limiting. This helps to prevent DDoS attacks by limiting the number of requests a user can send to an API within a specific time period. For instance, a user may only be allowed to view, like, dislike a particular video a certain number of times per minute. For a deeper dive into specific components or implementation details, leave a comment below or visit techstudycircle.com. Thank you for watching, and stay tuned for more insightful content on software engineering topics.